Now it is per unit area at a specific wavelength and per unit solid angle in a particular direction. In reality, no matter or no material is as good as the black body. Black body is an idealized concept and it is used for comparing how good or bad is the real material performance with respect to radiation. So the concept of emissivity comes up. Emissivity is the ratio of radiation emitted by the surface at a given temperature to the radiation emitted by a black body at the same temperature. Emissivity of a surface is given as epsilon. The value of this quantity varies between 0 and 1. This property emissivity is also never constant. Emissivity varies with temperature of the surface as well as wavelength and direction of the emitted radiation. Now there are two types of materials which are real materials and not ideal like black body. First is diffuse, which is defined as the material whose radiation property are independent in direction. Second is gray matter. This is the matter whose properties are independent of wavelength. Second is gray matter whose properties are independent of wavelength. So if we try to get a function of emissivity as if we try to plot emissivity as a function of wavelength, so in this direction it is wavelength and in this direction is emissivity. So let us consider black body. Black body, as you can see, it is a constant straight line. So there is actually no variation of emissivity with wavelength. But if you consider a gray surface, that is a dotted line here, for gray surface it is also constant with wavelength. But the emissivity is not equal to 1. For black body the emissivity is equal to 1. So gray surface also is an idealized concept where emissivity, although not 1, it is still constant with wavelength. But real surface, in that emissivity is neither 1 and it is also varying with wavelength. Black body is highest emissivity with constant emissivity independent of wavelength. Gray surface, although not the maximum emitter, but emissivity is constant with respect to wavelength. And gray surface and real surface is actually having emissivity changing with wavelength. So now we have studied emissivity. Now depending upon how a surface interacts with the incident radiation, different types of properties of that surface are defined. First is the absorbed radiation energy. When we say that a incident radiation is falling on a surface, the surface is shown here. This radiation can go inside the thickness of the material and get absorbed in the material. This is known as absorbed radiation energy, that is alpha Q. This radiation incident can also be reflected back. This is known as reflected radiation energy, that is RQ. And some of the radiation energy or rays can pass through the material and come out of it in the opposite direction. This is known as transmitted radiation energy, that is tau Q. So the total radiation energy incident can be absorbed, can be reflected, can be transmitted. So every material emits radiation and accepts radiation. The radiation that is accepted is either absorbed, which results in increase in energy level, or reflected, which results in radiation going elsewhere, or transmitted, which results in radiation passing through the material and going ahead. So there comes three properties: absorptivity or absorptance, reflectivity or reflectance, transmittivity or transmittance. Absorptivity is the fraction of irradiations absorbed by the surface with respect to total radiation. Reflectivity is the fraction reflected by the surface compared to the total radiation. Transmittivity is the fraction of radiation transmitted by the surface compared to the total radiation incident. So absorptivity is the ratio of reflected radiation divided by incident radiation. Reflectivity is the ratio of absorbed radiation to incident radiation. Transmittivity is the ratio of transmitted radiation to incident radiation. The summation of absorptivity, reflectivity and transmittivity is always 1. We have discussed fundamentals of radiation till now. There are many more concepts related to radiation, and if you would like to study in detail any fundamental heat transfer book like by Incropera David would be recommended for that. So now that we have reviewed fundamental concepts, let us move on to radiation modeling in Fluent software. We will first study some introductory concept of radiation modeling. Then we will see how to set up radiation model problem, and finally we will see details of important radiation models in Fluent software and boundary conditions related to radiation. First, let us see where do we use radiation models. It is not necessary to use radiations in all the simulation, mainly because if temperature difference between the hottest and the coldest points in the CFD model is low, that is below 400 degrees centigrade, radiation heat transfer is negligible compared to other modes of heat transfer like conduction and convection. So where do we observe high temperature, and hence radiation model has to be used in that case? There are cases like combustion modeling, automotive under hood, heating, ventilation, air conditioning, water treatment, glass applications where radiation becomes a compulsory phenomenon to be included. Radiation heat exchange is difficult to solve computationally. We have to have additional computational models other than the momentum equation and energy equation in order to capture radiation phenomenon.